So for the type of reactor and catalyst used, first we'll go with the type of catalyst used. So for this process, the type of catalyst used, or the most suitable catalyst of this process, will be PDSN catalyst supported on functionalized multi-wall carbon nanotubes. So why does this process involve the use of catalyst? So according to et al, Torani et al. 2016, in order to achieve concentration of 4-CPa in CTA of less than 25 ppm, which is the concentration that is required in order for it to be considered as pure TA, hydrogenation of 4-CPa impurities in CTA over a suitable catalyst must occur. On top of that, Wei 2013 and Hassan 2013 add that conventional hydrogenation catalysts containing active metals are commonly used for hydrogenation of 4-CTA. So these two statements show that hydrogenation of 4-CPA is a process that involves the use of catalyst. And why do we choose exactly PDSN catalyst supported on functionalized multi-wall carbon nanotubes as the suitable catalyst for this process? So, according to Torani et al. 2016, bimetallic catalyst with SN to PD molar ratio of 0.1 is a desirable catalyst for 4-CPa hydrogenation. Torani et al. 2016 showed that this catalyst had sufficient hydrogenation activity for 4-CPa hydrogenation, and the selectivity had significant increase from monometallic catalyst. So this is the reason why we've chosen specifically PDSN catalyst as the most suitable catalyst for our process. So moving on, what is the type of reactor used? So the most suitable reactor for hydrogenation of CTA, which is our process, is packed bed reactor. So why do we choose packed bed reactor as the most suitable reactor for this process? So first, according to the problem description, there's a flow in of CTA inside the reactor. So that means, or that implies, that a flow type reactor will be needed here because there's a flow in, so a flow type reactor will be used. So now we only remains to be seen what type of flow reactor will be used, because we have CTR, we have CSTR, we have PFR, and we have PBR. Those are the flow reactors we have. So which one of those we're going to use? So as stated by Wei 2013 and Hassan 2013, conventional hydrogenation catalysts containing active metals are commonly used for hydrogenation of CTA. So CTA, hydrogenation of CTA, is a process that involves the use of catalyst. So we have this information, and we have also the information that a flow type reactor will be needed in this process. So the flow type reactor that uses solid catalysts is PBR. So that's why the most suitable type of reactor for this process is packed bed reactor.
Hello, my name is MOISES. I'm from Group 2, and I'm here to talk about the description of the process flow diagram for PTA production. For the first step, we have the preparation of the solution, where we add the CTA, solid CTA, with water in the mixture with the stirrer. So we produce the solution of CTA. The stirrer present in the mixture is to accelerate the homogenization process. So for the second step, we have the reaction of reduction, where we have the solution for CTA reacting with hydrogen. This reaction converts the CBA into toluenic acid. And as a product, we have Ta, 4CBA, and toluenic acid. And for this reaction, we have a packet bag reactor where we use the palladium and tin catalyst and carbon nanotube as a supporter. For the third step, we have the evaporation, where the solution of Ta, 4CBA, and toluenic acid is put in a vaporization process to release amounts of water and to make the solution become more concentrated. The evaporation process is important also because it reduces the solubility of the solution, so making it easy to remove the crystals in the next step. For the first steps, we have the crystallization, where the solution, concentrated solution with less water, is put in the crystallizer, where we reduce the temperature and pressure to crystallize the PTA. And as a product, we have the solution, a liquor solution with PTA and water. And down here, we have the solids of PTA with 4CBA concentration less than 25 ppm. This is a very important process because it turns to be the major key of the whole process, because we get the purified TA. This is our main goal, to get the purified TA. So basically this is the whole process of the system. So thank you.
My name is Syazwan. So I'm going to talk about the strategy to maximize the selectivity and yield of purified TA. So to maximize the selectivity, we need to reduce the rate of reaction undesired product, and we need to increase the rate of reaction desired product. So the first step that we can do is by adding SN catalyst, it will reduce the decarbonylation rate of 4CBA, so it will increase the product selectivity. And the other things that we can use to maximize the selectivity is by adding the PD catalyst with loading of 0.3 weightage percentage. It will provide a sufficient hydrogenation activity for 4CBA hydrogenation without excessive losing of TA. And the third step we can do is by using large ratio of p-xylene during the reaction, we can it will produce large amount of p-toluenic acid. So huge amount of 4CBA will also be produced because of incomplete oxidation. So it will remove lots of 4CBA during the hydrogenation process, and it will produce large amount of purified TA. Next, we can recycle the 4CBA into the fresh feed. Why we can recycle it? Because it will increase the amount of 4CBA to go through again the hydrogenation process. The recycle process will increase the purified TA and will reduce the impurity content in the process. So it will maximize the desired product selectivity and minimize the unwanted byproducts. So the last thing that we can do is preparation of PDSN by SI method and SN over PD ratio of 0.1. So it will give us 99% removal of 4CBA and will enhance the process selectivity.
Sizing of the design reactor. These are all the information that we get from the article. First, the CTA is containing about 2100 ppm of 4CBA, 234 ppm of p-toluenic acid, and 50 ppm of benzoic acid with 280 ml of water. The given mass of CTA is 120 gram, with the mass of the catalysis is 1.3 gram. Next, the desired reaction to occur is at the temperature 290 degrees Celsius at 1 hour. The product should have an impurity of 4CBA less than 25 ppm. These are all overall chemical reactions that we get in the process of hydrogenation of CTA to PTA. And the overall chemical reaction that we get is CTA react with H2O and 3H2 to produce PTA. The mass flow rate of CTA that given to us is 30,000 tons per year. Then we convert it to the gram per hour and divide it with the molecular weight to get the molar flow rate. And the molar flow rate that we get is 20,614.07 mole per hour of CTA. Then we use the fourth step, which is first is mole balance. We find the mole balance for packed bed reactor. Then we identify the rate law. The third one is stoichiometric equation, and we combine the equation that we have and we find the new general equation, which is weight of catalyst is equal to Fa naught over mole of A reactant per time mass of catalyst, and time it with the conversion. Then we evaluate all the information that we have. First, we find the mass of the catalyst by using a ratio. Like we have a mass of the CTA over mass of catalyst. Then we have a mass of CTA that we have in the question, which is 30,000 tons per year, and we over with the mass of the catalyst. Like we use a ratio to find the mass catalyst, which is 37.10 kg per hour. From the mass of the catalyst, we find the RA, which is in the formula of mole of A reacted over time with mass of the catalyst. Then we get the RA is 555.635 mole kg per hour, and we find the conversion. We know that the product that we want is the impurity must less than 25 ppm. Then we assume as 25 is the maximum level. Then we find the conversion, and we find the conversion is 0.988. And from the conversion that we have by using the weight of the catalyst equation, we get the weight of the catalyst is 36.655 kg. Then we using a bulk density of PD, which is 20.02 kg per meter cube. We know that the density is equal to mass over volume. So to find the volume of the bed catalyst, we need to divide the mass of the catalyst with the density. We get the volume of the packed bed catalyst is 3.06 meter cube.
Now I'm going to talk about the type of separation system used to produce purified TA in crystal form. So the separation system that can be used is solid-liquid separation methods to separate and isolate the terephthalate acid product. A stage equilibrium crystallization approach is one separation method. The impurity concentration in terephthalate acid product is the lowest temperature to which the post-hydrogenation steam is flashed. The majority of terephthalate acid can be crystallized at a temperature higher than about 160 to 182 degrees Celsius, which is the threshold temperature at which p-toluene acid and co-crystallization becomes critical. By performing post-crystallization filtration at a temperature between about 121 and 149 degrees Celsius to obtain a p-toluene acid concentration of 150 ppm or less in the purified TA product.
I'm going to talk about the description on how the chosen separation system works for the production of purified PTA, including the operating condition. So there are two processes are included in this separation system, which is first evaporation in order to vaporize all the water, and then the crystallization in order to produce of purified PTA in solid form. So next, it is the assumption for evaporator. The first one is the term which is not elevation in temperature, and then the temperature at the feed is 240 degrees Celsius. The composition of CTA at feed is 0.95. Temperature at the steam stream is 370 degrees Celsius. Temperature at the reactor is 290 degrees Celsius, which is in between 240 and 370 degrees Celsius. And then the composition of CTA at liquid stream is 0.09. This is the diagram for the evaporator. So the CP we are getting at the feed is from the temperature of 240 degrees Celsius, and then the feed is assumed at 600,000 ton per year. The HS, the HV, the HL we are getting are from the steam table at respective temperature. So next we are going to see the calculation. In order to get HF, CP is done by delta T. The delta T is temperature at the reactor minus the temperature at the feed in Kelvin. And then in order to get the latent heat of steam of condensation, the heat of steam is minus the heat of condensate. And then in order to get L, we use the solid balance of CTA, and then in order to get V, we use the overall balance, which is F equal to L plus V. And then in order to get S, we use the heat balance and then the information that we are getting before. So for the crystallization, this is the assumption for crystallization, which is the temperature is dropped to 100 degrees Celsius, no water is vaporized, no water in the crystal stream. So this is the diagram for the crystallization. As you can see, the feed is from the liquid stream of evaporator, and then there is no water stream as at the assumption there is no water vaporized, and then at the C there is no composition of water, and then there is as the solution. So we are going to see the calculation of the crystallization. So in order to get the solubility of CTA, we are using solubility in water at 100 degrees Celsius. This is the 5.5 ppm, and then the 0.25 we are getting at the solubility table at the journal, and then the 0.03. From that, we can get the solubility of CTA, which is 0.0421 gram of CTA over 100 gram of water. And then from that solubility, we can get the composition of CTA, which is 0.042 divided by 100 gram of water plus gram of CTA 0.0421 in order to get the composition of CTA. And then in order to get the composition of water, 1 minus the composition of CTA. And then from there, we can get the solution, which is 3,454.1 ton per year. From there, we can use the overall balance in order to get C, which is 29,878 and 62 ton per year. That's all for me.
Hi, I am Nisrina, and I will explain the strategy to maximize the production of purified TA in the powder form. Significantly, we suggest two ways. The first one is to reuse the latent heat of the water vapor from the evaporator itself, and the second one is to adapt drying process in the production line. To define the performance of an evaporator, the steam economy, or in short we call as SE, is calculated to have a ratio between vapor produced and steam consumed. Higher SE value resulting in greater efficiency of an evaporator. However, SE can be improved in such way. Two primary ways to improve an evaporator's steam economy includes controlling the temperature by pressure change. This would lead to a multiple effect evaporator or recompression method. As studies were made, multiple evaporator and variation on the pressure will give higher result on the steam economy. Second strategy is to adapt drying process in the production line. As we can see from the diagram showed here, evaporation are limited to produce concentrated liquid only, while drying process are able to produce 100% solid content of product. Hence, these are the two ways to increase production of purified TA in powder form. I'll pass the floor to my friend.
So we have come to the end of our presentation. So for the reflection, first thing that I want to talk is what happened throughout this project. So actually, we need to do lots of research and some readings to answer all the questions that have been asked. And the second is, what were you thinking and feel? So while we were thinking how to complete this project successfully, and we feel pressured because we need to do lots of research to gain some knowledge to answer the question. So the third thing is, what was good and bad about the experience? The good thing is we learn something new and can be applied to our future in our future. And the bad thing about the experience is we face a lot of troubles and it stresses very much because we want to justify it to make it correct. So that's a bad thing about the experience that we have gone so far. So what sense can you make of the situation? So about this thing, we need to make a proper plan. We need to discuss in our group. So it will be easy to finish the project. So what else could you have done? So what have could we have I have done? Me and my groupmate do lots of meeting to make sure all of us understand the same things. So what happen if it arose again? What will you do? We so about this thing we need to meet lecturers to us to understand more about this thing. So I think that's all for the reflection part. Thank you and have a nice day.